I extend my heartfelt thanks to the organizer for inviting me to deliver lecture. Uh, I can't uh, uh, give you the name, but since I think but I am happy to say that one of my research scholars, till date I have supervised 37 scholars, and I have uh, I have another 4.5 years job. So 50 target is 50, 51, 52. Uh, so Dr. Bishal is one of them, one of those. And what sir is speaking, that is very sincere, working hard here. Listening it, I'm really happy because in my institute, in department, a very vibrating department now, Department of Mathematical Sciences, IIT BHU, and it is a good combination of senior and junior people. Generally, I devote my time from morning to night because my only wife is staying in Calcutta, so I get much time to devote for research. Actually, all scholars are my students, you know. So I am easily accessible. So I think that is the reason that they are doing very good works. Uh, you are in highly reputed institutes like IIT, Triple IIT, NIT, so and government colleges. So this is a success for us. टीचर को और क्या मिलना चाहता है तो कुछ नहीं मिलता कोई कोई भाव भी नहीं देगा उस समय बीबी भी भाव नहीं देगा इतना दिन साल बाहर में वो अभी आ रहे हो so now what is my talk today. Actually, I do research in 4 areas. One is fracture mechanics. Fracture mechanics, I did my PhD and postdoc in fracture mechanics. And this recipient in Gifford Memorial Award, actually, that is the postdoc degree in University of Calcutta. And my second area is mathematical modeling. Third area is porous media. And fourth is fractional calculus. Non-linear dynamics, sorry. Non-linear dynamics, dynamical system, neural network. So after, actually, when I joined IIT BHU, that time ITBHU, these are my students. So that time I had only expertise in fracture mechanics. Then I started to work in modeling, and I went to participate in a conference in France, So how the conference motivate us? You see, I'm just giving an example. Professor Chua, Leonard Chua, American Chinese. He was nominated 8 times for Nobel, but did not get. Circuit name is. After listening his here, I started to work. So sometimes you will get motivation from lectures actually. That's why conference is very much needed. Participation in conferences very much needed. Now, today I will deliver on the subject where I have completed 3 projects from BARC, Bioatomic Research Center. Consecutive 3 projects I got. The fourth one I'm going to get, that I've heard. So this is the area related to that one. Study of fractional order nonlinear transport phenomena problems in porous media. Means nonlinear. Now, today I will only discuss on the stochasticity. People say, what you are doing in fractional calculus sometimes. Are fractional calculus kya hai? Kuch nahi hai. Geometrical invention. I'm not interested of getting the or getting to know whether there is any geometric interpretation or not. Okay, I'm not interested. I'm not bothered. I will only analyze the stochastic analysis of the equations. Correct. So non-linear, semi-linear, it may be semi-linear, it may be quasi-linear, it may be highly non-linear. Okay. So rehabilitation, first 3 lines you just carefully consider. Rehabilitation will be very difficult if groundwater gets polluted in general. So it is important to model the contaminant. तो आज का सबसे बड़ा problem है contamination. The contaminant movement in aquifers to understand its impact on human health and environment. To accomplish this, a thorough understanding of physical, chemical, biological process of control, and it is needed. And after modeling, what is needed? After modeling, it is needed to have, you see, appropriate boundary conditions. Okay, without that, it is not possible. Because if you have d2y by dx2 plus mu squared y equal to 0, condition y equal to 0, y0 at 0, and y dash 0 equal to 0, you will get y equal to 0 is the solution. Because that is the trivial solution. To get the non-trivial solution, what we do? Use green function, bagada bagada. Correct, na? So sometimes appropriate numerical methods are also needed. Okay. So sometimes we use trial and method, this method, that method, we apply, but fail. Even sometimes it happens, we have taken the particular cases of the models, then analytical solution, and I have applied a numerical method. I have got good results, got publications. After 2 months, I see I have got another numerical technique through which I have solved the problem. I got better result, and I have got another publication. So it happens, correct? Now you see, in general, transport model are del C by del T is equal to, which is called like a diffusion equation. To D gets curve भी हम लोग grad बोलते हैं, the reaction term and advection term. The second term is the advection term, correct? Now you see, now coming to the fractional order system. Now what is fractional order? In most of the cases, people now today mathematical jugglery. कोई भी डेरिवेटिव देखता है उसको हटा के देता अल्फा 0 less than alpha less than equal to 1, 0 1 less than alpha less than equal to 2 fractional, correct ना? तो कितना jugglery होता है mathematics के. But here I have to convince the people ना it is appropriate, it is the right model, otherwise they will not give money ना. पब्लिकेशन तो हो जाता है इधर उधर करके, प्रोजेक्ट में तो पैसा भी मिलना चाहिए ना. How will get it? So this is the way we have to convince the people. What is written? The fractional order system of diffusion equation are obtained by replacing the first order derivative by alpha, where 0 less than alpha less than equal to 1. ये तो हाई हम भी admit कर रहे हैं. Next, an important phenomena is that it generates the fractional Brownian motion. Which is fractional Brownian motion? You know na? Motion. Which is integer order derivative, a differential operator is local operator. Whereas fractional order not, तो पकड़ने के लिए वो जो अमेरिका ड्रोन यूज करते थे ना, ऐसे गया ड्रोन मार के चला है, तो होता है. They had to take the statistics. क्या statistics क्या है? जो कम सिविलियन मरे एक इलाका को चुनते हैं, ऐसे करके कम सिविलियन मरे और मैक्सिमम टेररिस्ट मरे. इतना आइडिया ना. तो वो लोग कोई दिन का स्टैटिस्टिक्स लेता है. ओके, एंड दे ड्रॉ द ग्राफ ऐसे करके सब पॉइंट वाइज. नाउ दे टेक ए रफ पोजीशन. जैसे आप देखोगे आपको लगता है सब शहर में, आप जाओ कलकत्ता, आप जाओ मुंबई, आप जाओ चेन्नई, आप जाओ रोम, न्यूयॉर्क, फ्रांस, पेरिस, देखो उधर देखोगे सेंट्रल माने सेंट्रल कलकत्ता, सेंट्रल मुंबई मीन्स from where everything is available. You can get taxi, you can get metro, you can get buses. That is the central. That is the mean. केवल मीन का चारों तरफ कैसे और है, दैट इज द वैल्यू. तो वो लोग क्या करते थे, कुछ दिन का स्टैटिस्टिक्स ले लेते पूरा, ठीक है ना, लेके बारे वो लोग उधर से ड्रोन के बॉम्बिंग करते थे, ठीक है ना. समटाइम्स क्या होता है, वो लोग के पास भी, टेररिस्ट के पास भी खबर रहता है ना, दे विल अटैक थ्रू ड्रोन, वो लोग भाग जाता है ना. एक बार भी ये नहीं हुआ था, दैट इज कॉल्ड द फेलियर डेंसिटी. और होगा तो सक्सेसफुल प्रोबेबिलिटी डेंसिटी, दैट इज द वन. करेक्ट. नाउ क्वेश्चन है कि क्यों थर्ड मोमेंट निकालते हो, क्यों? Skewness means I am standing over here. You see, suppose I can see this. ऐसे करके देख सकते हैं ना, बहुत दूर से देख सकते हैं ना. Suppose मैथमेटिक्स में होता है ना, everything let I have two eyes, another two eyes at the back. अरे भाई कम से कम तो समझो, ये ले लो let. तो क्या होता है, खड़ा है, हम इधर भी जितना देख पाते हैं let. करेक्ट ना, that means symmetric ना, that is the Gaussian. That is the Gaussian. करेक्ट ना. सपोज हम थोड़ा इसे झुक दिए, क्या होगा, ज्यादा देखोगे कम देखोगे. नेगेटिव टेल इज ग्रेटर देन द पॉजिटिव टेल, दैट इज कॉल्ड नेगेटिव स्क्यूनेस. अगर ऐसे खड़ा रहो ज्यादा देखोगे. पॉजिटिव स्क्यूनेस एंड नेगेटिव स्क्यूनेस इज द स्क्यूड, नॉट सिमेट्रिक. सिमेट्रिक होता है जीरो स्क्यूनेस, दैट इज कॉल्ड गॉसियन ना. गॉसियन में होता है ना सिमेट्री. Fractional is not a Gaussian or does not follow Gaussian. This is the important phenomena of it. So fractional order system क्या है? Non-Markovian and non-Gaussian. This is the most important. एक बार आप लोग बोलोगे, तुम आए अच्छा होटल में रहे, अच्छा खाना खा रहे हो, साला इसे ही बोल के चला जाओ कि तुम कुछ मैथमेटिकल दिखाओ, मैथमेटिक्स दिखाओ. हाँ, एक बार मैथमेटिक्स आ रहा है. You see? Wherever I go, I start with this example. You know, this is the problem given in the book of Medhi, Jain Medhi, stochastic process, the Indian writer. आप देखोगे उसका बुक में है, आप देखोगे stochastic process and probability ज्यादा फर्क नहीं है. प्रोबेबिलिटी में क्या होता है, आप छक्का चालोगे ना, ऐसे होता है ना, क्या बोलता है, डाइस थ्रो करो, व्हाट इज द प्रोबेबिलिटी ऑफ गेटिंग 6? 1/6. आप इधर बैठ के मगध में करो, बेनारस में करो, मुंबई में करो और लंदन में करो, प्रोबेबिलिटी इज 1/6. करेक्ट ना. बट कभी होता है ना, सुबह बोला है ट्रेनर, तो ये मत दिल पर आम पर बचपन में हम लोग मारते थे ना, ढेला मार के आम गिर जाता है ना. सुबह सुबह क्या होता है, आलसी होता है, मारा, अरे मारे मारे, तो एक गिरा. आप देखो तो थोड़ा ये हो जाता है, तो 11-12 टाइम का क्या होता है, जोश ज्यादा बढ़ जाता है, उधर एकदम फटाफट लग जाता है ना, सक्सेस रेट बढ़ जाता है, कम था बड़ा. अब खाने का बाद नींद आ जाता है, तो क्या होता है, अब कम हो गया, अब कम हो जाता है ना. तो व्हाट आई वांट टू से, ये जो डिफरेंस हो रहा है टाइम का साथ, दैट इज द स्टोरी, है ना. इररेस्पेक्टिव ऑफ टाइम, इररेस्पेक्टिव ऑफ स्पेस, अगर होगा तो क्या होता है, दैट इज द प्रॉब्लम. बट इन स्टोकेस्टिक प्रोसेस इट डिपेंड्स ऑन द टाइम एज वेल एज द स्पेस. करेक्ट, ठीक है ना. हाँ. तो यही एक प्रॉब्लम है जहां आई हैव शोन स्टोकेस्टिक प्रोसेस में क्या, इन प्रोबेबिलिटी वी सी variance is very important, but in stochastic second moment is very important, means ex square is very important. If ex square is finite, ये क्या है, stationary process दे रहे, correct ना. If ex square is not finite, it will get evolutionary process. Sometimes देखो कि physics का लोग बोलता है ना, it is a evolution equation. What is evolution? I have studied a lot, and then I have seen it follows that ex second moment does not depend on the time, and you will be surprised. to see the next slide. Einstein क्या बोल के गए without knowing stochastic process. Just coming to that. Just coming. In Delal, uh, alpha is equal to 1 सोचिए. अभी अभी आप ज्यादा नहीं जाएगा उधर. Suppose alpha equal to 1 सोचिए. भाई बात मत करो. बात मत. Yes. I don't like that. Del u by del t is equal to del 2u by del x2. Suppose alpha is 1. ठीक है ना? Del u by del t is equal to del 2u by del x2. तो एक्सेस का क्या सेकंड मोमेंट इज t. तो क्या हुआ? इवोल्यूशनरी इक्वेशन. आइंस्टाइन के टाइम में people did not have idea about the what do you call evolutionary stochastic. Einstein was told that he is the first who told that it is the evolutionary equation. Second moment depends on time. Second moment depends on time. Einstein, without knowing the stochastic process, and you see that becomes a subject. How visionary he was. Whatever he used to say, that became a subject. Correct. So now, I have assured you, I will not say anything जो bogus होगा कि कहाँ भी alpha चढ़ा देगा, or you will say that this is a fractional. No. What I will do, I must justify it mathematically. Correct? You see, ये 11th में था. अब देखो, ये फिक्स लॉ है ना, फिक्स लॉ नॉन फिक्शन ना, फिक्स लॉ था ना, हम लोग 11th में था ये बंगाल बोर्ड में. आप देखो फिक्शन J is equal to minus D into del U del X. What is D? Diffusion. नेक्स्ट लाइन देखो, del U del T is equal to minus del J by del X. इसको क्या बोलते हैं? मास बैलेंस इक्वेशन. By J is the flux, है ना? अब बीएससी में कहाँ भी था ना. हाँ, अभी दोनों को मिक्स करो. J का जगह माइनस डी इंटू del U del X. ये थोड़ा गलती हो गया. तो del U del T becomes D into del 2U by del X. ये गलत है ना, जल्दीबाजी में आना था ना, रिपेयर कर दिया था. del 2U by del X2. So del U del T is equal to del del 2U by D into del 2 by del X2. What it becomes? Diffusion equation. Correct? Fiction. Following the fiction law. Non-linear हो जाता तो non-fiction. ठीक है ना? देखो एक चीज I say, J. Suppose linear equation follows. अच्छा next अभी नहीं बोले. Now अभी देखो ये भाई विशाल that time तुम्हारा thesis में है. This one हम स्टडी कर रहा तो हमारा थीसिस में वाला मिला था. If you take a closer look of fraction fixed law Norwood 1972, you see the बोलता है ना आजकल फ्रैक्शनल आजकल रिसेंट है 10 साल. You see, suppose look up that one and gamma alpha minus 1. गामा फंक्शन आप लोग जानते हैं ना, इंटीग्रेशन 0 to infinity x to the power n minus 1. हम टाइम रहते थे और बोलते थे गामा फंक्शन के एक क्या होता है, तो गामा फंक्शन ऐसे होता है राइट में. गामा 0 does not exist, गामा minus 1 does not exist, गामा minus 2 does not exist. करेक्ट ना? गामा minus 1 गामा 0 माने गामा फंक्शन exist everywhere except 0 minus 1 minus 2 minus 3. ठीक है, but 1 by gamma alpha exists everywhere. It is a continuous function. हम लोग बोलते हैं ना tan 90 does not exist. कोई बच्चा को पूछो बोलेगा tan pi by 2 कितना? Infinity. tan pi by 2 does not exist. You see in a graph pi by 2 minus is plus infinity and pi by 2 plus is minus infinity. So it is infinite jump. Does not what the mathematical calculation हम लोग क्या करते हैं? It takes as infinity. Correct now? Gamma 0 does not exist, but 1 by gamma 0, 0. We take 1 by gamma 0, 0. Similarly, gamma minus 1 does not exist. 1 by gamma minus 1, 0. So if you draw a graph, you see gamma. So what will you prefer? Gamma n or 1 by gamma n? 1 by gamma n is preferred. Correct ना? So आपका कैलकुलेशन में वो भी मैथमेटिकल कैलकुलेशन गामा एन नीचे आएगा यू आर सेफ, बट गामा एन अगर माने ऊपर में आ जाएगा तो बड़ा कभी कभी 0 -1 -2 है ना, हमारा क्वेश्चन हो जाता कंटिन्यूटी का। एनीहाउ, सो वो मिला के देखा, नाउ मास बैलेंस इक्वेशन इज डेल अल्फा u by del t alpha equal to d into del q u del x. So even in the first time when I delivered this one in bar, I had to convince तुम दिखाओ मॉडल। So now we'll appreciate now the del u by del t can be converted to del alpha u by del t alpha where 0 less than alpha less than equal to 1. Huh? If alpha is integer, alpha is 1, then original equation. If 0 less than alpha, then mean time. Fraction. Now तो एक हम स्टोकास्टिक सेंस में क्या बोलेगा? जियोमेट्री तो हम नहीं दे सकते, लोग बोलेगा बकवास काम है, ये सब फालतू ये सब लेके कर रहे हो, हमको तो कुछ देख के लोग को कन्विंस कराना है ना। नाउ आ रहा है स्टोकास्टिक एनालिसिस, करेक्ट? You see, let us consider del alpha u by del t alpha equal to del t u by del x to minus infinity less than x less than infinity. ठीक है? अरे बाबा x का डोमेन आ गया, t का डोमेन आ गया, t तो नेगेटिव नहीं होता है, ठीक है ना? तो देखो लीनियर इक्वेशन होता है, माने हम सोचना बच्चा का बोलते हैं जे लैप्लास फूरियर का कहाँ ये है, ड्रॉबैक्स कहाँ है? लैप्लास ट्रांसफॉर्म, फूरियर ट्रांसफॉर्म, हांकेल ट्रांसफॉर्म, ड्रॉबैक है these are the linear transform. माने if you want to apply on the differential equation to solve the differential equation by using Laplace transform, what you have to do? It has linear. Non-linear नहीं होता है, non-linear को Laplace फूरियर हांकेल all क्या है बोलो मानते Laplace ये linearity property hold करते। So it is a linear equation, so I am applying the Laplace transform. Laplace transform operate कर दिया, ये आई एस टू द पावर अल्फा u x u bar x is minus dot 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 all and zero ले, ठीक है ना? So what I have got u bar x is equal to as into which is unknown a, ठीक है ना? ईडी एंड ओडी में डिफरेंस क्या है? ओडी में जो कांस्टेंट आता है वो सिंपली कांस्टेंट, ईडी में कहता है डिपेंडेंट ऑन सम अदर वेरिएबल, सो इट विल बी इसका ऊपर होता है। इसका बाद ऐसे बोर्ड में करते तो अच्छा लगता है। हाँ, ये बात देखो, प्रोबेबिलिटी डेंसिटी फंक्शन का डेफिनेशन क्या है सब लोग जानता है, तो प्रोबेबिलिटी कोई ना कोई बोले माइनस इनफिनिटी प्लस इनफिनिटी u x is equal 0 1 probability density function, तो I have applied that one. देखो एकदम सिंपल आइडिया, एकदम सिंपल, कोई ये नहीं है। बिकॉज हम देखते हैं अंडर ग्रेजुएट पढ़ाने का बाद ना कुछ पेपर होता है ना, बहुत अच्छा लगता है, बहुत अच्छा हो जाता है। हाँ, अंडर ग्रेजुएट से सीखोगे ना, और सीखना है तो स्कूल लेवल में 11-12 पढ़ाओ, क्या मैथमेटिक्स है, करेक्ट ना? सो व्हाट विल गेट अब टू केस मैंने मोमेंट, उधर मोमेंट निकाला ट्रांसफॉर्म डोमेन में। समटाइम्स क्या होता है जान, तो लोग बोलता है क्यों, हमको स्टूडेंट पूछते हैं सर व्हाई वी यूज द लैप्लास ट्रांसफॉर्म, व्हाई यूज द फूरियर ट्रांसफॉर्म, व्हाई द नीड ऑफ ट्रांसफॉर्म। क्या होता है जान, तो और समटाइम्स क्या होता है, सपोज हम पढ़ाई कर रहे हैं, करते एक कैलकुलेशन नहीं हो रहा है, सडनली बाहर गया, अरे बाबा बाहर गए, आके सडनली स्टक इन माय माइंड, अरे ऐसे करने तो होता है, तो देयर इज नो पेन एंड पेंसिल, पेन एंड पेपर्स। हम लोग क्या करता है, वहां पास चला आता है, घर में आके करते हैं ना। तो जहां गया तो ट्रांसफॉर्म डोमेन, जहां स्ट्राइक किया, तो फिर हमको इधर आना है डोमेन, टाइम डोमेन, फ्रीक्वेंसी डोमेन, करेक्ट ना। तो दो डोमेन होता है, ठीक है ना। तो लिटरेचर में देखोगे बहुत से प्रॉब्लम बड़ा बड़ा मैथमेटिशियन, बड़ा बड़ा फिजिसिस्ट का सॉल्व हुआ था टॉयलेट में, टॉयलेट में सोच रहा है। एंड आई वांट टू शेयर वन थिंग, लास्ट ईयर में आई वेंट टू कैम्ब्रिज यूनिवर्सिटी। देयर इज वन न्यूटन इंस्टीट्यूट, न्यूटन 5-6 है ना, तो न्यूटन इंस्टीट्यूट हमारा लाइफ में सब। एंड प्रोफेसर जे.आर. विलिस इनवाइटेड मी, हु इज द एफआरएस, फेलो ऑफ रॉयल सोसाइटी। तो वो न्यूटन इंस्टीट्यूट में टॉयलेट में बुक पेन सब कुछ है, मतलब अगर किसी को मतलब ये होता है तो लिखेगा। यू सी, हम सोचा था हमारा डिपार्टमेंट में हम लगाएगा टॉयलेट में, कोई बोला अरे गाली फाली लिख के चला जाएगा, क्या जरूरत है। तो अब देखो कल्चर, तो ठीक है ना। तो 2K ले आए, एंड यू सी द सेकंड मोमेंट, लास्ट में देखो सेकंड मोमेंट रेसेस विद p to the power alpha नॉट फाइनाइट, मतलब क्या है, इवोल्यूशनरी प्रोसेस। तो क्या हो गया है, इवोल्यूशनरी प्रोसेस, नॉन मार्कोवियन, नॉन गाउसियन एंड इवोल्यूशनरी। नाउ यू आर कन्विंस ना। अभी जाके फ्रैक्शनल में कुछ काम करना, लोग अगर बोलेगा तो बोलना ना, वो बोला था इसे, ठीक है ना। ये बात देखिए, कभी कभी होता है ना, तो थोड़ा एम्बिशियस हो जाता है, अरे कुछ मिला और कुछ मिलेगा, शेयर में जैसे लगाता है। आज 1 लाख लगाया, अच्छा आए, मैं तक समझ में हुआ था ना, कल 5 लाख लगा दिया, कल 10 लाख लगा दिया, बस गया मार्केट डाउन ना। तो रिसर्च भी हम लोग शेयर में लगाता है वैसे ही। इक्वेशन का और बढ़ाओ, दो कुछ दिन बाद आ जाएगा, एडिटर लिखेगा व्हाट ए रबिश पेपर यू हैव सेंट। लेकिन अगर एक्सेप्ट हो जाते तो अच्छा होता है ना, बोलेगा हमारा एक्सेप्ट हो गया पेपर, बच्चा को पीएचडी भी हो जाता है। तो वैसे ही हमें किया, ठीक है ना। तो आई हैव रिटन, हाँ जेपी जी देखिए इधर, इसको स्टोकेस्टिक एनालिसिस कर रहा है। नाउ क्वेश्चन होगा, why you are only applying the stochastic analysis on linear equation, why not non-linear equation? Because linear अगर सुनिए, अगर linear अगर what I want to God has created the integer, अब सुनो, God has created the integer, else is done by the man. ये था ऑडेसिटी था, आप देखिए, God created integer, else is done by the man, he told, माने so that Kronecker product I've applied, correct ना। so ये सब if people are interested, okay, आप लोग देख लेना जो Kronecker प्रोडक्ट में कैसे यूज किया, अगर आप लोग का इंटरेस्ट है तो, ठीक है ना। so many calculations are there, and finally I have done। हाँ, another thing, आप जितना भी बड़ा कैलकुलेशन करो, no one will accept in research। what you have to do, you have to show the particular मॉडल का particular केस लेके whether वो वैलिडेट हो रहा है कि नहीं यार, आरडीएस जो रिजल्ट है उसको साथ मिलाना है, हाँ यही है ना। then only the people will accept, validate, you have to validate your result, correct ना। so what I've done, I have taken a particular form, literature survey करके उसको देखा है, and they are very pleased, you know, तुरंत ये बहुत बड़ा जर्नल में छापा है। तो ये देखो 10 to the -4, 10 to the -6, 10 to the -8 होता है। देखो कभी कभी हमको भी लग जाए publication, whatever I got the publication, so it is very good paper, not that, sometimes क्या होता है जानते हो, आपका जाना पहचान का बात चला गया, क्या होता है, वो उस दिन अच्छा मूड में था, बीवी का साथ झगड़ा नहीं हुआ, किसी का हस्बैंड का साथ झगड़ा नहीं हुआ, पॉजिटिव रिपोर्ट दे दिया। उल्टा होता है तो झगड़ा हो जाता है तो तब करते नहीं है, बीबी के ऊपर गुस्सा नहीं दिखा पाएगा, चलो इसको काटो पेपर को, ऐसे वो भी होता है ना। तो आई एम नॉट टेलिंग दैट constant. So sometimes क्या publication is somewhere? No. But you are thinking sometime. You are thinking sometime, you are writing. अगर आप उसको भेजो तो एक कंट्रीब्यूशन तो रह जाते हैं ना, अगर एक्सेप्ट होता है ना, तो आप वही सेंस में सोचो जो रिसर्च पब्लिकेशन जरूरी, ठीक है ना। तो अनदर थिंग आई डिड इट, करेक्ट ना। ऐसे एक मॉडल भी किया था, बहुत सारे डिफरेंट मॉडल RW। यू सी हाउ मच नॉनलीनियर। जेपी जी देखो इधर W इतना है, ये देखो RW है, so it is quasi linear, correct। Next step we did it highly non-linear, del U del T squared, and all have been accepted. My last project was I just submitted a report and 10 published papers. They are very happy, and they have promised me they will give another project. Actually क्या होता है जानते हो, प्रोजेक्ट हम लोग का ना यूनिवर्सिटी व IIT सिस्टम नहीं होगा, नंबर 1 प्रमोशन विदाउट क्या बोलते हैं, प्रोजेक्ट नहीं देते, हमारा प्रमोशन क्या है, सब कुछ तो हो गया, ठीक है ना। हम लोग को प्रमोशन चाहिए, क्या हम लोग का क्या चाहिए, कुछ पैसा, इतना सारे बच्चे, इतना बड़ा लैब, हमारा लैब है, लैब को चलाने के लिए, ठीक है ना, पैसा चाहिए। और अभी तो हेड है, छुपा छुपा के कोई कंप्यूटर खरीद लेगा तो कोई समझ भी नहीं पाएगा ना, हेड लोग करते ना हमारे उधर, छुपा के कंप्यूटर ले लिया, छुपा के ये कर लिया। आई डू नॉट डू दैट वन, आई डू नॉट नीड दैट वन। तो वैसे भी हो सकता है, फिर भी प्रोजेक्ट जाते हैं तो काम होता है ना। तो आप लोग प्रोजेक्ट लिखिए, एंड यू नो, और मैट्रिक्स प्रोजेक्ट अभी तो अच्छा पैसा कर दिया, 25 लाख, हम जब मिला था 6,60,000, अभी तो 20 ना 6,60,000, अभी अच्छा कर दिया। DRDO दे रहा है, इसरो दे रहा है, ये दे रहा है, यू राइट ना। those who are in university college level they should write the प्रोजेक्ट लिखिए, देगा फंडिंग एजेंसी, क्यों नहीं देगा, सब देता है, ड्यूरेशन भी बढ़ा दिया, ठीक है ना। तो देखिए हम बड़ा बड़ा मैथमेटिक्स बोल के चला जाएगा और सोचेगा क्या बोल के गया, आप लोग बोलेगा अरे क्या बोल के गया, कुछ नहीं होता है तो इट इज काइंड ऑफ इंटरेक्शन। हाँ तुम्हारा प्रोविसी गुस्सा हो गया ना, कंक्लूड बोलना वैसे गुस्सा हो जाएगा तो अच्छा नहीं लग रहा है बोलना, अच्छा लगता हो नहीं, आप लोग का बात सुनेगा नहीं, मैडम बोलता है हम सुनता है तो व्हाट आई एम सेइंग, दिस इज अ काइंड ऑफ so I think next time क्या बोले, हम सुनेगा आके, आप लोग भी आओगे तो इधर जे कोई फ्रैक्शनल में काम किया, इंस्पायर्ड होके, दैट विल बी आवर सक्सेस ना। सीनियर रिसर्चर क्या करेगा ना, तो होपफुली नेक्स्ट टाइम माने हम लोग सुनेगा, दो एक कोई रिसर्चर बोलेगा हाँ हम फ्रैक्शनल में किया, मोटिवेटेड बाय यू, ठीक है ना, वही सक्सेस है ना। क्योंकि बड़ा बड़ा एग्जाम्पल दिखा के, ये दिखा के सबको तो ये नहीं होता ना। सो न्यूरल नेटवर्क मेथड इस ये वाला बहुत चल रहा है, न्यूरल नेटवर्क मेथड, इट इज कनेक्टेड टू दैट न्यूरल नेटवर्क, बट इट हैज, माने इसको ऐसे देता है। आप देखो न्यूरल नेटवर्क मेथड करोगे तो आजकल पब्लिकेशन बहुत ईजी है, डिफरेंट मेथड। तो एक है ऑपरेशन में, क्या जानते हो, ऑपरेशन मैट्रिक्स मेथड। लास्ट 5 इयर्स में करीब 800-900 पेपर आ गया, वह नहीं चलेगा, नया मेथड करना है, नया मेथड, ठीक है ना, न्यू मेथड, हाँ ठीक है ना। सो दिस इज काइंड ऑफ दिस वन। तो फाइनली I have to stop saying that. No. Problem is not neural network. Problem is PD. The method name is neural network. हाँ, उसको अंदर में न्यूरॉन का जो आइडिया होता है ना, न्यूरॉन का कनेक्शन होता है ना, वो मैट्रिक्स को इसे करके लिख रहा है. That is, method is related. You can use this method to the neural network problem. Correct ना? The problem is PD. Correct. So कहाँ भी मॉडल नया करना है, ठीक है ना? न्यू मॉडल करो, तो न्यू मेथड करो, कुछ तो करना है ना? Otherwise तो people will not accept your work. This is the kind of method what you have used to solve a non-linear fractional order problem. Okay? Thank you.
Thank you, sir. I'm very pretty sure, sir, that there will be research scholars who will be doing work in fractional mathematics. I'm sure, sir. Thank you very much. Now I'd like to call our head of the department, Dr. Sunil Suman, sir, and Kumar Vishal, sir, on the stage to felicitate Professor Sudhir Das, sir. Sir, you also on the stage, sir. Vishal, sir, you also come on the stage, please. Because that is a moment, a supervisor and a scholar together. That's a moment. Huge round of applause. Thank you very much. सर आपसे जो मिला है वो कुछ भी नहीं है जो हम दे रहे हैं. थैंक यू सर. Now it is my honor to invite on stage our next distinguished speaker for his invited talk. His name is Dr. Jay Prakash, Associate Professor in Department of Mathematics, BHU Varanasi. Dr. Jay Prakash earned his PhD from IIT Kharagpur and later pursued postdoctoral research at the prestigious Technion Israel Institute from Israel. His primary research lie in fluid mechanics, especially flow through porous media, and various other application of mathematics he is also working. He has served as a visiting professor at École Centrale, Paris, and has been the recipient of several notable research awards, including the PBC Postdoctoral Fellowship from Government of Israel, Matrix Grant and Co-Research Grant from ANRF. ANRF से रिसर्च ग्रांट मिलना बहुत बड़ी बात होती है. हम लोग अभी भी ट्राई कर रहे हैं, नहीं मिला है. तो मैं आपको जो बोल रहा हूं उसका मीनिंग है, कोर ग्रांट मिलना, मैट्रिक्स ग्रांट मिलना बहुत बड़ी बात होती है. सर के पास 3 है. And he has more than 30 publications in highly reputed journals. Dr. Jay Prakash continues to shine significantly in the advancement of mathematical research. Please join your hands together to welcome Dr. Jay Prakash on the stage. Please, sir.
Very good afternoon, all of you, and thank you, the organizers, especially Dr. Roma. It's my privilege to be here and an honor to deliver an invited talk here. So the thing is, there are two types of people, you know. There are people who work hard. There are people who hardly work. Okay. Here, I have seen the people. So they have organized it so meticulously. Fantastic. I mean, thank you for invitation and congratulations to the entire team.
Credit goes to head, sir.
Okay. So, am I audible at the back? Okay. So I think I don't need mic then. Do I need? Okay. So As you can see, to hold. Okay, so we have listened to many people, right? Since morning, you listened to the inaugural event. There were people they spoke about application of mathematics, and then we had keynote by Professor N.R. Paul, and then by Professor Suvidas. You must have seen one term that was common across all the talks. Any name? I mean, particular term. Or did you hear something called mathematical modeling? If you paid attention, you would have noticed. Everyone, not everyone, I mean, in the forenoon session, when we had inaugural session, some people spoke about mathematical modeling. Then Professor Pal also said something about mathematical modeling, and then Professor Suvidas also said mathematical modeling. Something. I mean, he showed different equations and all, but all of them, there was this term, common term, mathematical modeling. What is it? I mean, what is mathematical modeling? When I say mathematical modeling, what do you, what goes in your, into your mind? What is mathematical modeling? So, what I feel is mathematical modeling is it's an art. You know, it's an art to portray something. I mean, any physical problem. Let's say I say, okay, you throw a ball. You throw a ball. Let's say at some height. What will it do? It will go up to some height, right? And it will go on and on until it reaches certain height where it has zero velocity. Okay, and then it starts falling down. So if you had to come up with certain equation, that okay, the height equation, how much distance it covered, and then what is the velocity at a particular instant, and many things. So there are few things that you would tend to neglect. For example, somebody, I mean, air has friction, right? I mean, I don't know. You must have studied something statics and dynamics. So when you model some equations, you consider whether there is air resistance is considered, taken into account, or it is not. So while modeling certain things or any physical quantity, or you say uh, pendulum, motion of pendulum, simple harmonic motion. Yeah, you know, right? The equation. So what are the parameters that play a role there? Gravity will be there, length of the string will be there, and then the mass of the pendulum. Those things are there, right? So there are effects that are very significant. They don't affect your assumption, whatever you're trying to find out. But there are some parameters, or there could be some parameters that are small enough, but they are significant. You cannot ignore them. So, as the title suggests, perturbation method. So, perturbation method is one of the methods to solve nonlinear equations. Okay, linear equations. I mean, you know several well-known methods. If you have ODE, you know several methods. I mean, you can solve them, or if not, you can write any differential equation, any ODE as a system of first order ODE. That you know, right? I mean, we call them as a simultaneous differential equation. There are other things. I mean, whether it is autonomous, non-autonomous, I'm not going to go into that. But what I'm saying is, if you have linear differential equation, you can. There are methods available. You have seen all the methods. You can solve them. But when it comes to nonlinearity, there are some nonlinear ODEs that you can solve. I'm forgetting the name. Some Cauchy, something is there, right? You do some substitution kind of thing, and then you can solve that equation. But beyond that, there are equations that you cannot solve. But when it comes to PDEs, it becomes even more challenging. So if it is linear, you solve them. There are methods, you know, up to second order, at least you know the methods. How do you solve them? But if it is non-linear, then it becomes challenging task. What are the methods? Either you go for numerical techniques, you know, right? I think you must have studied in your master's finite difference method. finite difference method पढ़ा है, एटलीस्ट सुना है, नहीं सुना है? हाँ, तो finite difference method, not just the finite difference method, there are other methods, finite element method, finite volume method. There are even more methods, finite, there is something called boundary element method, then there is something called radial basis functions and all. Mesh free method they are called. So they will give you numerical solutions, but the perturbation method, it gives you approximate solution. So I have one question. I mean, if you can answer, what do you think? If you have exact solution of an approximate model, that one you would go with it, or you have approximate solution of an exact model? Which one do you think? I mean, you would go with? Exact solution of an approximate model, an approximate solution of an exact model. कौन सा लगता है कि हाँ ठीक है? Which one? What is that? Second, I mean, I don't know which order I mentioned. So, exact solution of approximate model, and approximate solution of exact model. Approximate solution of exact model, right? So, if you have a non-linear system, so forget about getting exact solution. It's very difficult. So you can only find out approximate solution of that particular equation, whichever equation you have. So before we go into this, so perturbation method, there are some terminologies that you need to know. If you have seen, that is called big O order symbol. So if I say I have a function f of x is equal to x and f of x is equal to x square. When x goes to 0, which one will decay fast? Obviously x square, right? But how do you say that certain function is of this order or that order? So there comes this order symbol, the notion of order symbol. And what is it? So let me just give you. Then I'll come to this point. How does it work? Okay, so it is what I just mentioned. So most of the problems that come across, all the real world problems, they are highly nonlinear in nature. I mean, of course, we make certain assumption and then you simplify your model just to have an idea, qualitative behavior. You will get a qualitative behavior, but so based on that qualitative behavior, you can actually find out the solution if you, at all you make an attempt to solve your actual model. So to solve actual model, you'll have to have either some numerical technique or this one. Okay. So it says perturbation is to determine the behavior. So perturbation theory, you use certain parameter, that's very small parameter. So you look at the behavior when the parameter goes to 0. Okay, the parameter goes to 0, so obviously it will. So when parameter goes to 0, call that as an unperturbed problem, and then you write down the equations at each order, leading order. You call them as leading order, first order, second order, all those things. But since your parameter is very small, you cannot consider a second order or third order and beyond, because your parameter is so small that all the higher powers, they will not contribute much. You can neglect them. So where do we have to neglect them? At which order we have to neglect them? That's where this comes into picture. What is the order symbol? So here. So we have to define order symbol. So there are two symbols. It is called big O, little o. What are they? So big O is, sorry. So the first one is called big O order. You can say f is of order phi if the limit epsilon going to epsilon 0, f of phi by phi of epsilon, f of epsilon by phi of epsilon is finite. And then there is little o, the second one, it says the same thing, but the limit has to be 0. Okay? And then there is something called asymptotic solution. What is that? We say that f is of, asymptotically, it behaves asymptotically as equivalent to phi if f of f minus phi is of the order little order phi. Okay, so these are the things that you need to take into account when you are dealing with perturbation method. So these are some of the concepts. So when you come to this perturbation method, there are two types of perturbation method. One is regular perturbation and the other one is singular perturbation method. It's not very easy. Regular perturbation problems are where you are using regular perturbation methods. They are easy to tackle with. When I say easy to tackle with, that means you find out your solution to the problem using this perturbation technique and look at the behavior when that perturbation parameter goes to 0. What happens? Qualitatively, it agrees with your unperturbed problem. So, for example, if I say x square plus, let's say, 2 epsilon x minus 3 is equal to 0. It's a quadratic equation. You can find out the roots, right? I mean, using the formula. And if I say, okay, I want to solve it using perturbation technique. So in perturbation technique, you take them as a what do I call, as a series in terms of in powers of epsilon. Epsilon is the perturbation parameter. So you take x is equal to x naught plus epsilon x1 plus epsilon square x2, so on and so forth. And then substitute in your actual equation and compare the equal powers of epsilon to get the equations at each order, leading order. So the equation that is independent of epsilon, that will be called as leading order, and then first order, second order, you solve them. And then you add them up and then take the limit when epsilon goes to 0. That should agree. So in actual equation, if I have x square plus 2 epsilon x minus 3 is equal to 0, if you substitute epsilon equal to 0, what do you get? You get x square minus 3 is equal to 0, x is equal to plus or minus square root of 3, right? Same thing you will get when you solve using that perturbation method. X naught plus epsilon x1. So you find out the solution for x naught, you find out the solution for x1, x2, plug in them in the series, and then take the limit epsilon goes to 0. You will see that that agrees with the same thing, whatever you got. X naught is equal to, x is equal to plus or minus square root of 3. Whereas in singular perturbation, if I say, okay, I take epsilon x square plus 2x minus 3 is equal to 0. Okay, it's a quadratic equation, right? But what is happening when epsilon goes to 0? When epsilon goes to 0, what will happen to the equation? I have the equation epsilon x square plus 2 epsilon x minus 3 is equal to plus 2x minus 3 is equal to 0. When epsilon goes to 0, what will happen to the equation? The quadratic term, it will vanish, isn't it? X square term will vanish. So what is happening here? You are losing out the information because your actual equation is of second degree. But when you are taking the perturbation parameter, you are letting it go to 0. You are losing out the information because your order is being reduced. I mean, from second degree to you are getting to linear. So you are on the information. So these kind of problems are difficult to solve. So here there are something. There are called some transformation. You have to use some transformation. They are called some stretching variables and all. Then there will be some overlapping region where you need to match. In that particular region, you need to match the behavior. You need to see the behavior, what is happening in this particular region. So singular perturbation problems are not easy to tackle with, whereas regular perturbation problems are easy to tackle with. That is the whole point here, because what I am going to present here is the regular perturbation problem. So how many of you, are actually working in fluid dynamics? Anyone? Any? cannot be negative. It has to be between small parameter. 0 to 1, yes. No, you cannot afford to equation y double prime plus y is equal to 0. What is the solution? Y double prime plus y is equal to 0. What is its solution? Cosine x plus sin x? I mean, a cosine x plus b sin x, isn't it? It hoga. So what does it represent? It represents oscillation in the solution, because sine and cosine, they are oscillatory in nature. They wavy type of equations. But let's say your system hands that, okay, I want these oscillations to die out as time progresses. What do I do? What would you do? I mean, see, I want, okay, I have some system where there are oscillations and all, and I want the oscillations to die out after certain amount of time. What would you do? You would add resistance or something called damping. And damping is nothing but, it's in terms of velocity. You multiply by some constant and then subtract it from the equation. So if you have equation y double prime minus y prime or plus y prime plus y is equal to 0, find out the solution. Or y double prime plus 2y prime plus y, that is equal to 0. What would be the solution? Then you get the solution as e to the power minus t, and that's cosine t plus sine t, all those things will be there. But when t goes to infinity, what will happen? Because e to the power minus t is present in your system, that will make your y vanish when t goes to infinity. So it depends what is your requirement. I just gave one example, but it all depends on your requirement. Somewhere somebody might want something to include, somebody might not want to include something. It all depends on your requirement or the requirement of the physical problem. What is it that you are trying to solve? Okay, I hope I answered it. So I was talking about this equation. They are called Navier-Stokes equation, and they are, the first one is still open problem, $1 million problem. Raised by Clay Institute, Mathematics Institute in the US. So they had proposed some 9 problems. They were open problems. That means nobody had solved them. So the problem here is that existence uniqueness of the solution of Navier-Stokes equation in 3-dimensional space. So nobody has done it. It is still open problem. So $1 million. You crack it, you get $1 million prize money. Okay. So, but people have been working numerically and then are using some perturbation parameters, perturbation technique and all. They have been using. So as you can see, there is one parameter, this RE you see, right? That is called Reynolds number. So actually Navier-Stokes equation, it is nothing but force balance. It comes from conservation of momentum. So it is actually force balance. So there are, so the last term that you see, that is called viscous force, because when fluid flows, it flows in layers, and there is friction between any 2 layers. That friction is called viscosity. I mean, water is there, water hai, drop karo, honey drop karo. कौन सा जल्दी गिरेगा, कौन सा बाद में गिरेगा? Honey, right? Because the friction is too high between the layers. The viscosity is very high or high for the honey compared to viscosity for water. Okay? And then there is some this second term, the first term on the right is called pressure gradient. That is also, I mean, it's a force acting on the surface per unit area. And then on the left, the first term is called unsteady term, and the second term is called inertial term, where the velocity interacts with its gradient. Okay, I mean, this is one equation. The other equation you see, equation number 3, they look similar, but the difference is the number that you see. Here you see the RE is called Reynolds number. It is nothing but actually viscosity, the ratio of inertial to viscous forces. So it depends. What is it that you want to consider? Somebody wants to consider very high viscosity. So that means your viscous forces will be dominant over the inertial forces. RE in that case will be very low, will be small. And if somebody wants to consider the inertial forces, that means viscosity is the inertial force, viscosity is going to be 0, approaching 0. Obviously, the Reynolds number will be very high because it is sitting in the denominator. Viscosity is sitting in the denominator. So what will happen? That is called ideal fluid. I mean, that reduces to Euler equation. All or Bernoulli equation. You must have heard about it. If not now, plus 2 में सुना ही होगा Bernoulli equation. So, first one governs the motion of fluid. Second one governs if you have a fluid and there are some solute or something you mix with it. That will also, it will not only diffuse, it will at the same time, or you just see, you take a bucket or you look at a canal where water is flowing, you put a dye. Put dye, what will happen? The dye, it will start diffusing at the same time, it will start being convected along with the velocity of the flow in the canal. So this is nothing but it is called convection diffusion equation. Okay, and then again, as I said, Re here P also gives the same way. Diffusion ratio of the convection to diffusion. Okay, so which one is dominant? Accordingly, P takes the value. Okay, and then similarly there is for heat transfer. Same, they are analogous. Heat and mass transfer, they are analogous. The only difference is that, okay, in one case you have concentration, in another case you have temperature. Okay. Okay, so this problem is actually motion of droplets or bubbles. So there is something, it's called Taylor-Kuwait flow. You have a cylinder, put inside another cylinder, and then the cylinder rotates, the inner cylinder rotates with some velocity. But when this velocity reaches to a critical angular velocity, what happens is, and when you inject the bubbles, so there are some vortices, they are formed. I mean, how do I put it? Because or there are some disturbances. Or you look at your wash basin sink, you open the tap, and then you look at the sink, the outlet. You see what kind of disturbances are there. There will be some vortices. You must have seen this whirlpool kind of thing, no? देखा है ना? Wash basin, you open the tap, and the velocity is high. You look at the outlet, where the draining system. What happens? It is some kind of whirlpool. So that is called velocity. और ये भी देखा होगा ना? Dust storm में देखा होगा जो क्या बोलते हैं उसको? आधी आती है वो बाउंडर क्या बोलते हैं? हाँ, whirlpool. So that will be formed, and then what happens? The interesting thing. So I should have mentioned, when Re is very small, when Re is much less than 1, then that non-linearity will be gone and it will become a linear equation. That is called Stokes equation. So linearity, the property of linear equation is that you can split into two sub-problems and you can use principle of superposition, because linearity gives you that liberty. Whereas if it is non-linear, you cannot use the principle of superposition. Superposition तो पढ़ा ही होगा आप लोगों ने. Principle of superposition क्या है? वो linear combination बोलते हैं ना? You use the linear combination. So principle of superposition you can use. So what happened was, for droplet or bubbles, if you take, so let's say I don't know whether you have realized it. I take two plates. One, the lower plate is fixed and the upper plate is moving back and forth, and then the gap is filled with some liquid. Okay, so obviously the motion of the plate will generate flow. That will be kind of a driving force. Okay, so and then what happens? There are some, so it is called shear flow. The kind of flow that is generated, that is called shear flow. And then if there is some bubbles, and then it is called streamlines. Streamlines, if you have some particle, it cannot go beyond the streamlines. It has to follow certain path. Okay, but there were two guys, so it has to follow the streamline. That means it cannot go across the streamlines. Let's say streamline are flowing this way, and particle is sitting somewhere in the center line, it cannot, it has to move this along the flow direction, not perpendicular to the flow direction. But what happened, there were some people who performed some experiment and they observed this thing that, okay, the bubbles, they move across the streamline. But then it is not possible when you have a linear flow or a linear equation, Stokes equation. So their question or their hypothesis was that, okay, the inertia is playing a role. So inertia is the culprit here. Okay? And that is playing a role in migrating the droplet across the streamline. So this is what we also observed. There was an experiment by these guys, Segre and Silverberg. They performed this experiment and they observed this phenomena. Okay, what is happening? I mean, how do I get rid of this? Yeah.
विशाल को बुला दो, विशाल को। वहां से ब्लू वाला से।
Cross it. Yeah, remote नहीं है, उधर से अमर।
वो ब्लू वाला जो गोल है ना, उसको चाहिए ना, उसको चाहिए। हाँ, उसको चाहिए, उसको चाहिए ना। अरे हाथ रखिए ना इसे, उस पर चढ़ेगा। तो उल्टा सीधा करा है। ये जो ब्लू वाला है ना, इसको हाँ, अब देखिए क्या करना है।
PDF, no? Yeah. Okay. So here I was talking about this cylinder, right? You take a cylinder, you put inside another cylinder, and the inner cylinder you start rotating. You give it some angular velocity to the inner cylinder, and then when its angular velocity exceeds some critical angular velocity, at that moment you inject some bubbles into it. So as you can see, so there are, so this vortices I was talking about, right? You look at the drainage system and then there will be some kind of whirlpool and spiral and all. So these are vortices, and then there will be some bubbles. You see on the right, there are blue colors that are trapped inside vortices, and there are pink color bubbles. They take position inside near the inner wall. We are not interested into that. We are interested only though in those bubbles that are entrapped in those vortices, and they form this ring. So this is from the side. Next one I'll show you. This is from top. So all these droplets or bubbles are monosize. When I say monosize, they are of equal size. So from top you see, what do you see in first one on the left? There are two bubbles. So they take equal position, okay, equidistant. 3 position, they form equilateral triangle. 4, they form vortices of a square. And 5, so on and so forth. Irrespective of the number of bubbles, the separation distance between any two bubbles is same. Okay, irrespective. I mean, doesn't matter how many bubbles are there, but the distance is going to be always same. So 3 bubbles, they will form equilateral triangle. 4 bubbles, they will form vortices of square, so on and so forth. But what is the reason? And then it is stable ring. So the previous case I showed you, right? It is ring. So then the question is, why do we see this? Why do they tend to distribute uniformly, irrespective of their numbers? So again, I said in simple shear flow, the bubbles, they don't experience any force. So you cannot see such kind of phenomena. So our hypothesis, by the way, this experiment I didn't perform. I developed the theory behind it. So so we also propose this hypothesis that okay, these bubbles, they tend to distribute uniformly, and the culprit is inertia. So it is driven by force. Obviously, there has to be some force that is maintaining them at a particular distance. Okay, and that is due to inertia of the flow. This is what was our hypothesis. And due to their interaction also, because there are bubbles, they will talk to each other. Okay, so an interaction also, it can be seen differently. You can say, okay, I mean, each bubble interacts with its neighbors, nearest neighbor. So let's say there is this bubble, I mean, sitting, and then one is on the left, one is on the right. So it will interact with both of them. So nearest neighbors. Other is pairwise interaction. You say that, okay, there are n bubbles. Each bubble interacts in pairs. So this interacts as if the others are not there. And then you come back to the first bubble, and then you say that, okay, it is a periodic. So there are three types of model. So I'll come to that. But this is what it is. Okay. So our aim was to experiment, to explain this phenomena that was observed in the experiment. Okay. So, and by the way, this was published, and this is my postdoc work. So it was appeared in Physical Review E. I mean, it's one of the journals. Okay. So here is a simple model. I have taken two bubbles at some distance. Okay. So here the case is, I said, okay, they experience some force, but how do we calculate that force? Because now I'm going to consider the inertia. So the Reynolds number, I said perturbation method, right? The Reynolds number is going to become my perturbation parameter in this case. And I have assumed that, okay, it is very small, but not zero. Okay? It is small, but not zero. So that Reynolds number is going to become my perturbation parameter. So to solve this, because I am only interested in finding out the force. To find out the force, instead of solving the nonlinear equation, I'll propose something called auxiliary problem. I'll not be using that problem anywhere, but the solution will be used to find out the force. And to find out the force, this theorem will be used. It is called Lorentz reciprocal theorem. It's basically, it says if you have two different problems, different boundary conditions, so they are related through this integral. Okay, and this integral is going to give us the force. Okay, so now my equation is this one. I excluded the time dependence and all. Time dependence I have excluded, and then this is viscous force. I mean, you must have seen the Reynolds number, and this one, and the second equation is called mass conservation. Okay, and then these are the boundary conditions. So you see, I have taken only up to Reynolds number, order 1. Okay. Order R is square and beyond I have neglected, because at that particular instant I could find out. So I didn't feel that, okay, I should go for the higher order, and it's not an easy task. It is very complicated. So these are, so similarly, velocity, pressure, and stress. Sigma is called stress tensor. Okay. So you can express them. And these are the conditions. So the leading order, V0, P0, when you see that superscript, they are nothing but the leading order. So leading order, you see V0 plus RE, V1. V1 is the first order velocity. P1 is the first order pressure. Sigma 1 is the first order stress tensor. And sigma 0 corresponding, all the zeros are the leading order. Okay. So these are the equations. So leading order satisfies Stokes equation. That is linear. So here we have, I mean, we are okay with it. The problem comes at the first order. This one we can solve, but when so there are different coordinate system. I mean, I think you must have heard about this all these special coordinate systems, spherical coordinate system, cylindrical coordinate system.
पता नहीं क्या
Sorry? There are many. I mean, I can name them. Spheroidal coordinate system, ellipsoidal coordinate system, then toroidal coordinate system, tangent coordinate system. Which one do you want? Here, there are two particles, multi-particle system. So you cannot use your conventional coordinate system like spherical coordinate system. You cannot use. You can neither use spherical coordinate system nor cylindrical, or forget about Cartesian. So there is some special coordinate system. It is called. I mean, these are the equations. So you see now on the right, for the first order problem, on the right, you have some equation, some terms are there. By the time you reach the first order problem, you will know what is right hand side, because the leading order V0 will be known to you, and V infinity is far field velocity. I mean, that is something. I mean, at the far field. Okay. So here the reason is, why do we have to solve the auxiliary problem? So I said I'll propose one auxiliary problem. I'll solve that one instead of solving this entire thing. I don't have to solve the first order problem really. Because I'm interested in only finding out the force acting on these bubbles. So here you see this is the equation, and then you have to use simple Gauss divergence equation. Gauss divergence theorem is there, right? Convert double to triple and all those. And use them to find out force, and then you see that these bubbles, they experience force equal and opposite. So one bubble is there, the other bubble is there. They will experience the same force, but they will be opposite in direction. Okay, and it will be repulsive in nature. So I was talking about special coordinate system. So this is bispherical coordinate system. Okay, so when you are dealing with multi-particle system, you cannot use any of the conventional coordinate system like spherical or whatever. I mean, you know them. So bispherical coordinate system, this is, and they are connected through, I mean, there is some transformation. So any coordinate system, you can relate to the Cartesian coordinate system using some transformation. Okay. So here also it's the same thing. And then these are the expression. And here, the problem here is that you have all these infinite series. You cannot find out the solution of infinite series. So problem is here again, how do we find out the solution? So it has been established that this converges uniformly. So, but numerically when you are solving, you cannot say that, okay, I should truncate at n equal to how many terms I should consider. Whether I should consider 50 terms or I should consider 100 terms. It all depends. So what you do is, you write your system, write some MATLAB code and all, and then check for your solution for n is equal to, you truncate the series at n is equal to, let's say 100 terms, and check it for 120. If you are getting the same result, then you can say that, okay, I have reached the convergence. Beyond it, doesn't matter whether I consider extra terms or not, it's not going to change my result. Okay. So the bispherical coordinate system, it gives you exact solution, whereas, but I want to know the evolution of the separation between the bubbles. For that, I need to have some differential equation that I cannot get using bispherical coordinate system. So for that, I have used one method. It is called method of reflections. It gives you approximate solution, but it gives you a closed form solution. So where you can write down in terms of differential equation and all. Okay. How much time do I have? Over.
You can over.
No. I'll just then I'll run through the slides. Sorry. They are equal size bubbles. Yes. Mass I am neglecting. Bubble. What mass? No. Here angular velocity. That is gone. That is gone. That I am interested only in the why the ring is formed and what is the distance between each bubble. That is going to change with time. No, this is just for your graphical representation. Okay. So what I'm trying. So see, you have ring. I'm saying right. You cut it at one place and just unwrap it. What will happen? No. Bubble. No. If it's distance. No. Initially, you'll give some initial separation, right? then that separation evolves with time, and there will be a time that is called relaxation time, where each bubbles, they will be placed equidistantly, uniformly. They will be placed uniformly. Bubble, I mean, you cannot. It doesn't have any mass, so you cannot include the rotation of the bubble. That is ruled out. That will not be coming into picture. Because you're considering, hold on, you're considering solid body, right? In solid body, you cannot exclude the rotation because it has got certain mass. But bubble, whereas bubbles, it doesn't have any mass. So if you are considering rotation of a bubble, I mean, anybody would say, I mean, it's rubbish. As sir pointed out, you send it to some, you work on it, send it to journal, the editor will throw in dustbin. I mean, it's all rubbish. Okay. So that is not there. Okay. So what I'll do is I'll run through the slides because I'm running out of time. That's what your organizer is saying. Okay. So I'll just run through the slide. I'll show you the results. So this is method of reflections. I mean, it's like, okay, so you have two different coordinate systems. I mean, R1 theta, spherical only, but different. R1 theta 1 phi, R2 theta 2 phi. And then there will be some relation between R1 and R2. And so the idea here is you solve for one particle or bubble, assuming that the other is not there. So you do it, let's say R1 theta, for R1 theta 1 phi, and then similarly you solve for R2 theta 2 phi. But now when both are there, the same boundary condition, you cannot say that, okay, the boundary condition will be satisfied at this boundary and the same boundary condition is going to be satisfied on the other boundary. That's not going to happen. So in that case, you'll have to take the reflection. So reflection from one particle to the other, and from this particle to the other. And it depends how many reflections you take. So this is what, so you see the conditions, and those indices, they represent reflections, number of reflections, how many reflections you have taken, okay? So this is the velocity that you get. Yeah, who's calling? No. So yeah, this is auxiliary problem, again I have solved, but for the, using the method of reflections, okay? And then the force, you see, bispherical gives you exact solution. Hold on. The second order, also I have considered two reflections, first order, second order. So second order reflections, you see. So obviously when D is the separation distance between two bubbles. If D is small, then there, because method of reflection, it is going to give you approximate solution. It is not going to give you a better solution. But as D increases, then you see they agree. Okay. You see when D is beyond 10, they agree very much, very well. Okay. So this is all bubble dynamics, the evolution of separation. How do we find out the evolution of separation? So obviously there is a force that is due to the inertia. That is due to the inertia and then their interaction. So what I'm saying is I have to look at the evolution of this. I have to make use of some force balance. So I'm saying that this inertial force is going to be balanced by a viscous force. I mean, for droplet or bubbles, there are standard results available. So this balancing will result in a translation of the droplet or these bubbles. Okay. So that translation I can always write as dl by dt. Velocity I can write dl by dt. Right. So that is what is the case. So I propose three models: nearest neighbor interaction model, pairwise, periodic model I was talking about. Okay. So these are the three differential equations that you'd get. L1 is, let's say, two bubbles, so separation between the separation distance between these bubbles. Okay, center of the bubbles. So that is, so for each case I have, and then you can find out, and then you see monotonically, the largest one decays monotonically, but the intermediate one, non-monotonic behavior. Okay. Similarly, this is for 4 bubbles, and you can keep doing it. And this is comparison with experimental data. So you see, so these are the experimental data, and then the blue dots on the right, you can see that are nothing but from the experiment. So you can see that they actually follow whatever we develop the theory. They follow the pattern. Okay. So this is similarly for 3 bubbles, 4 bubbles, and somebody can say, what is this? The negative side. I mean, some negative time and all it is showing, right? That you cannot control, because when you are injecting the bubble, you don't know the actual location. Okay, in the experimental, so that is an experiment. Right hand side, it is our theory. Okay, so this is what. I mean, actually, I had 2 problems, but due to lack of time, I'll stop here only, because there are two ways to use the perturbation. One is you use the perturbation in the equation itself. The other one is you can use the perturbation in the geometry. Let's say I said, okay, these bubbles are spherical in shape. I say, okay, no, they are not. They are some deformed shape. So the deformation that you can consider as a deformed shape, you can take as a parameter, and then from there you can bring in again the regular perturbation and then find out the solution and all this. So this one I have used. So here, so bubbles can be, so the center one is spherical. It is called spheroid, roulette and oblate. Okay, roulette and oblate. And method, whatever I had derived, this is applicable to any kind of geometry as long as you know the equation of that geometry. If the equation is known, you can use this method to find out, I mean, the relevant thing, whatever you are interested in, using this technique. Okay, so this is what, and then this is also published. This was published in Physics of Fluids. I'll stop here because.
थैंक यू वेरी मच सर, थैंक यू। आप लोगों को बता दूं कि ये जो पढ़ा रहे थे, ये मैं पढ़ने की खुद कोशिश कर रहा हूं। इन्होंने एक ही क्लास लिया मेरा, और बहुत से क्लासेस बाकी हैं। इज अ वेरी गुड रिसर्चर एज वेल एज अ टीचर। थैंक यू वेरी मच सर, थैंक यू। नाउ आई वुड लाइक टू कॉल डॉक्टर सुनील सुमन सर, हेड ऑफ द डिपार्टमेंट, टू प्रेजेंट मोमेंटो to Jayaprakash sir. No, this is post presentation memento, sir. And our research scholar, especially Raja, has made an effort to make this memento. And the one that you are having is official Angvastra of Magad University and official memento. Thank you, Jayaprakash sir. Once again, okay. Quickly moving to the technical session. हमें पता है कि आप बहुत डिले हो गए हैं हम लोग, लेकिन हम लोग टेक्निकल सेशन कर रहे हैं। आपको पता है, आपको शेड्यूल दिया जा चुका है कि किसका कहाँ होगा, आज किसका होगा। We are having 2 parallel sessions, right sir? We are having 2 parallel sessions. One is going to be here, मतलब एक यहाँ होने जा रहा है, और दूसरा पैरेलल सेशन हमारे कंप्यूटर लैब में हो रहा है। आप सब लोगों को ग्रुप में पहले ही इन्फॉर्म कर दिया गया था कि किसका कहाँ पे होगा, ठीक है। कुछ लोगों का आज है, कुछ लोगों का कल है। आज मैं इस क्रम में सबसे पहले बुलाना चाहूंगा डॉक्टर जीनत परवीन को। डॉक्टर जीनत परवीन, और मैं इसका अगला जो है वो भी बता दे रहा हूं, लेकिन इससे पहले कि आपको बुलाऊं, कोई भी टेक्निकल सेशन तब तक पूरा नहीं होता है जब तक उसे कोई चेयर ना करे। एंड टू चेयर दिस सेशन I would like to request Dr. Manish Kumar Singh sir to come to the center stage. Dr. Manish Kumar Singh sir. He will be chairing the session, and it is up to him when he is going to